Hello everyone, welcome back to our subject Computer Organization and Architecture. So in today's topic we are going to discuss about influence on instruction sets and data path and control considerations. Okay, so this is the last topic in our third unit, and it is a continuation of the pipelining concept. So previously we have seen in detail about hazards in instructions, is it not? Before that, earlier we have seen about data hazards, structural hazards. Okay, and here we are going to see about influence on instruction sets and data path and control considerations for implementing the pipelining. Okay, so we need to make modifications in the hardware organization so as to apply the pipelining concept. So otherwise previously we have seen about hardware organization for single bus and 3-bus organizations. So there we need to have some modifications so that hardware organization will accommodate the concept of pipelining. Okay, and moving on to this, these two are very simple topic. Okay, and it's quite easy also. And the first topic we are going to see about influence on instruction set architecture. Okay, so computer systems will differ instruction set one and the other. Okay, so in that situation, so how to handle the pipelining concept when there are some different during the different aspects we need to consider for different computer system architectures. Okay, so some instructions will be well suited for pipelining, and some other instruction is undesirable, that may have side effects like data dependencies. We have seen about push and pop instructions, add with carry, and some conditional code flags. Those will depend on for those instruction data dependencies are high, and those are said to be side effects in pipelining, because that will introduce stalls in pipelining, and due to stall the performance of pipelining is degraded. So somehow we need to manage it so that the instruction the best suited instruction for pipelining we need to take into account to get the high performance. Okay, so that's the topic we are going to see it, and we are going to examine about two aspects of machine instructions. Okay, addressing modes and conditional code flags. So these two things we are going to see how different addressing modes will how the different addressing modes. So when discussing about the addressing modes, we have seen about auto increment, auto decrement, register, indexed, relative, so all in for direct or indirect versions. Okay, so some addressing modes are well suited for pipelining, and some have some side effects that needs to be avoided, and condition code flags, both we are going to see it in today's topic. Okay, so first discussing about the addressing modes in different computer systems that may favor for pipelining, and some of the addressing modes that may not favor for pipelining. Okay, so when speaking about addressing modes, we have complex addressing modes and simple addressing modes. Okay, in choosing the addressing modes for pipelining, we need to consider this two aspects. This two will affect the performance of pipelining. Okay, so one is the side effects, and the other side effect means data dependencies like add with carry instruction, push instruction, pop instructions. Some of the instructions we have covered already about the side effects of pipelining, and the extent to which the complex addressing modes can cause the pipeline to stall. Okay, so complex addressing mode may introduce the stall, and how extent we need to use it, and how to use the alternate approach, because the complex instructions sometimes may not give good performance. So without giving if the instruction is not giving performance in the pipeline, means why we should go for taking that instruction into pipelining concept. So if we take, means definitely it will introduce the stalls, is it not? So that kind of instructions should not pipeline. Okay. And complex addressing mode, we are going to take this example and we are going to compare it with the simple addressing modes, okay, with pipelining. Load x r1 to r2. So here this is quite complex. What we are doing, since it is given in parenthesis, you will be knowing the meaning. So r1 within the parenthesis means r1 has content. That content is not an operand, that content is an address, okay, and that address is added to this index mode. So x is an index variable, x plus suppose I'll take the example as if r1 is of an address 1000 means, and x is of value 20, okay. So what does it mean? We need to add to get the address, okay. So this is one address, and this is again given inside the parenthesis, outside parenthesis, is it not? So what does it mean? So this 1020, if you go and fetch in the memory at this location 1020, it will give one more address, okay. So it may be something, for simplicity take one more value as 2000 as an address instead of an operand. Then again the second parenthesis, what it says, again we need to look into the address location 2000 in the memory, okay. So this is a complex, a little complex, okay. So see here how this instruction is executed under pipelining. Fetching and decoding, no issues, only in this calculation purpose, because we only during the execution stage of the pipeline the calculations are happening. So here this calculation will happen. For this calculation it will take one clock cycle, and so here next to fetch this in address 1020, we need to fetch its content, and the content is and the content returned as 2000. So for this to happen, we need one more clock cycle, and in 2000 we need to get the operand value, is it not? For that we need one more clock cycle, okay. So 3 clock cycles we need to execute this instruction, and finally whatever the value it is there, that we are going to store it in the R2 register, okay. And due to this the next instruction is stalled for 2 cycles, because it takes 2 more extra cycles to fetch the instruction from the memory due to this complex addressing, okay. So if we use the forward operand forward, we could have due to this operand forward we could reduce this stall to 2 cycles, I mean 2 stalls, 2 one. So this cycle 4 and clock cycle 5 are stall, okay. Only 2 stalls when we go for operand forwarding, okay. Operand forwarding means you will be knowing, so taking the executed value to the next stage, instead of taking that executed value to store it in the register and taking again back to here. So it will introduce one more stall if we won't use the forward operand forward means, okay. So this is about complex addressing modes. So to execute this instruction we need how many 6 clock cycles, is it not? And so we will consider how the same instruction if we split up by having the simple addressing mode. This instruction is splitted into 3 instructions. So this three code will do the same, both are same, okay. So this is we are saying as an simple instruction. So here when we execute this simple instruction, add, what we are doing, add the offset value 20 to 1000. So 1020 will be in R2, and go and fetch 1020. So in 1020 we will be having 2000, and in those go and fetch the year 2000 value. In 2000 address location we will be having the operand value, and that is finally stored in R2. So this instruction is this complex instruction is splitted into 3 instruction, and we are executing the same in the pipeline and see the final outcome. It takes how many? 1 2 3 4 5 6 7 clock cycles, and previously whether I missed out for the next instruction. Yes, again in complex addressing mode also this instruction takes 6 clock cycle, and for the execution of the next instruction it takes 7 clock cycles. Okay, so here also in simple addressing mode the execution of the next instruction starts at clock cycle 7, and similarly to execute this 3 instruction it needs same clock cycle. There is no difference between complex addressing mode and simple addressing mode, is it not? When both the thing gives the same when both the instruction complex instruction and complex addressing mode and simple addressing mode, if both gives the same clock period means, then why should we prefer complex addressing mode? Because for complex addressing mode we need a complex compiler to identify and fetch the correct information, is it not? So we need a little additional hardware to understand that instruction. So why would we go for preferring that one when we achieve the when we don't have any good performance due to that complex addressing mode, is it not? There comes the question, is it not? Then so that's the thing we are going to see. Complex addressing mode, how it is effectively increasing or whether it is giving any stall when we implement the same in pipeline concept. Okay, so in pipeline processor, so complex addressing mode do not necessarily lead to faster instruction, is it not? Yes, we have seen both the complex and simple instruction both gives the same clock period. It takes 6 clock cycles to complete. Then what does it mean? The complex addressing mode is not giving the fast execution. So only the advantage of moving to complex addressing mode is we could reduce the number of instructions, and due to that reduction it will occupy less memory space, because there it is one in complex addressing mode there is one instruction, and to achieve the same execution of that instruction in simple addressing mode we need 3 instruction. So we need to store 3 instructions in the memory, is it not? So in simple addressing mode memory space is high, and only advantage of that complex addressing mode that we have seen is all about reducing the number of instructions and saving the memory space. And the disadvantage is, so long execution when we we have seen about 2 stalls were introduced, and here simple instruction we don't get any stalls. So of course both will execute the same time. There it introduced the stall, and it needs some complex hardware to decode that complex addressing mode, and that will be a burden for the compiler to do that operation, is it not? And finally the conclusion of using the complex addressing mode in pipeline is not much recommended or not well suited. Okay, and the good addressing mode must have these features, and these features are not given by the complex addressing mode, and let's see what those features are. So access to the operand should not go more than one cycle. So that is the one of the good feature of an addressing mode. Whatever the addressing mode if we use, that should not take more than one clock cycle to fetch the operand. Okay, and only load and store instructions are recommended to access the memory operands. Okay. So load and store instructions have the direct access to memory, and addressing modes used do not have side effects. So the addressing modes like we have seen auto increment, auto decrement. So those are side effects, and of course those are also not recommended for pipelining. Okay, those instructions are not recommended to execute in under pipelining. So if we execute those instructions, then it will introduce a stall, and if a stall comes, then the performance gets degrade. If the performance get degrade, then why should we go for pipelining? So that's the basic question arises when we go for having the instructions that has side effects when we implement in pipelining. Okay, and so these are the addressing modes. The register indirect and index addressing modes are highly preferred to implement pipelining, because these three will go for this feature. Okay, these three will take the above said three features, and it is the recommended addressing modes to be implemented in pipelining. Okay, so that's about addressing modes. Then addressing modes in the instruction set, and how it is influencing the execution of the pipeline. And the other one is conditional codes. Conditional codes means when we do some calculation, say take for simplicity addition. After addition, so what will happen when there is a change, when we perform addition, and when we get the result as a negative, when the result of the addition is negative, the processor will store the separate special register, okay, to store the outcome of this addition operation. Okay, so what that outcome, if the outcome is supposed to be of negative value, means that flag n will be set in that processor special register, and if the result happens to be of all 0, means the processor will maintain a bit for storing that in the Z register. Then whether that addition happens to have overflow or not. Likewise, some of the registers carry or carry. So if a result produces a carry, means those informations will be maintained by the processor using the condition using some special register, and that we are saying as a conditional code flags. These are the flags, so that each flag will take one bit to store its information, either yes or no. So if whether the result is 0 or not. Likewise, we have seen already, we have covered this in the previous topic itself, I mean the previous unit. And here in pipelining, how these register values will affect the pipelining concept. Okay, so due to this conditional code flag, the execution of the next instruction will definitely affect, is it not? So we need to reorder the instructions. A program is of many instructions, is it not? So we must have a sophisticated compiler technique. Okay, so if an optimizing compiler attempts to reorder the instruction to avoid pipelining stall because of branching and data dependencies. So pipelining stall occurs when the instruction happens to be of branch instruction, or there is a data dependency due to this flag. Also due to this flag, the outcome of the next instruction will definitely gets affected, and it may take one more extra clock cycle to identify what's happening, is it not? This conditional flags has to be read so as to decide which instruction has to execute next. So this will also introduce the stall, and to avoid that stall, we need to reorder the instructions, so that that delay slot can be occupied by some other instruction, so that without a delay we could achieve the better performance. Okay, so that's the concept of conditional pipeline. And see here a very simple example and a clear cut example I have given, which is given in your textbook, to reorder the instructions so stalls could be avoided. What stall is? Stall is nothing but an idle stage of a pipeline, it means it does no operation, and because of that one clock cycle is wasted. Okay, and see here, this program fragment, in the sense part of the program, not the complete program. So we have three instructions: add, compare and branch. Okay, so what's happening after add? So, and of course you can see here the registers involved R1, R2, R3, R4. There is no data dependency. It means the result of R2 is not applied here in this compare. So these two are independent, can execute independently because there is no data dependency. That also has to ensure when we go for reordering. Okay, so see here, in the second line we are comparing R3 and R4, and based on that comparison, if we get result 0, so comparison will always give the value true or false. It means 0 or 1. If it happens to be 0, means we need to branch to somewhere else. So this branch instruction depends on this previous outcome. Okay, and see here, so this one, due to that we have seen compare, immediately the branch, it will introduce two stalls in our pipeline execution. Due to that, compare and immediately the branch instruction, and we have covered already. It's okay, then I'll cover again. It's like a just a quick recap of that. So compare, it gives the result at cycle 4, and see here, branch. In the branch we have the decode and target address, we are getting it, but this target address is dependent on the previous outcome. So we will be getting the previous instructions result only at 3, cycle 3, and that cycle 3, after that cycle 3 only we will be getting the result. Based on that result, the branching will be calculated. Simultaneously, while these things are happening, instruction 3 and 4 are fetched, is it not? And what happens if the outcome of this instruction is somewhere to here, the instruction k? So these two instructions I3 and I4 has to be discarded, and it introduces the 2 stalls, is it not? So the same thing, if we rearrange the instruction compare, add, branch. So what will happen? While comparison is taking place, instead of let it be there itself. So here if we introduce add, okay, so instead of this instruction, let it be the add. So yeah, what will happen? Add will do as usual. So here fetch instruction, decode, execute, write to will happen. Okay, so at that time, excuse me, so write 2. So this is, I am discussing for the this code. Okay, so I am overwriting there to make it clear understanding for you. Okay, so if it is of that add instruction, so add instruction will go as usual, and the result of I1 will be available at cycle 3, and here the branch will happen. So just omit this, instead of I3, now our branch instruction will happen. So fetching the branch instruction, decoding it, and we will get the, after decoding we will get the execution of the branch instruction immediately. Okay, so no need to wait till see here, I think here in this stage itself, D3 itself, we will get the branch target address. Okay, so here itself we will get, because at clock cycle 3 only we are getting that comparison result, and that can be given in this decode stage itself, because we have the specialized decoder that will decode the instruction and also identify the branch. Okay, so simultaneously at clock cycle 4, the other instruction, take an example as here, the other instruction 3 is executed. So and what happens if it is supposed to be of instruction k, the target address, instead of I3, means only one stall is introduced. Okay, so when we reorder, so one stall is introduced. So when we don't reorder, 2 stalls are happening. Okay, so reordering definitely will increase the performance of the pipelining. Okay, so that's what we are going for, reordering the instructions. And of course we need to the compiler, it's up to the compiler to have the utmost care that reordering should not affect the program outcome. So it means here the operands are independent of each other, is it not, so that we could reorder it. What happens if if R2 result is utilized in R3, I mean R2 result is needed for comparison like R2 comma R4. In that situations we could not, the compiler won't prefer reordering because of data dependency. So that care has also be taken by the compiler. Okay, so the main logic behind here, the conditional codes, what it's a conditional code means, here checking the condition, branch condition, and because of that without reordering two stalls are happen, and when we reorder one stall has happened, it means we have saved one stall, and it means the performance is though degraded, it is much better when compared to execution of the same instruction without reordering. Okay, the conclusion is to provide flexibility in reordering, the condition code flag should be affected by as few instructions as possible in the program. Okay, so it should be limited, the condition code flag affection, because when there is a frequent conditional code usage means that will introduce stall, at least one stall, is it not? So that should be of some limitations of having the conditional code flags in our program, and the compiler should be able to specify which instruction produce the condition code and which is not. Okay, so these two things has to be taken into account for increasing the performance of the pipeline. So that's it about the influence on instruction sets. So how instruction set influence the execution of the pipeline. Okay, so we have seen about only addressing modes, and the second one is condition code flags. Okay, and next to implement the pipelining we need to consider the data path in the hardware organization and how the control signals are generated. Okay, so this is also quite interesting and easy topic. Okay, so we have seen earlier about the 3-bus organization, this one. So this one, so 3-bus organizations where we could fetch the register values parallelly at a time to the ALU, and the output will be given to this another bus C. We have covered already this topic, so please pay close attention to these components. So we need to rearrange it somehow to implement this bus organization in pipelining. Okay, so while implementing it the data path gets modified. So why we need to go for modification? Because we need to avoid data dependencies. Okay, so when the hardware is designed in such a way of more dependency means we could not implement the pipeline. So in 3-bus organization it doesn't consider about that pipelining concept. So when we apply the same for to take into account of pipelining means we need to have modifications in that organization to achieve the pipelining concept. Okay, so see here the same organization is modified over here with different flow. Extra things we have is in this hardware organization we have a separate instruction cache. I think it could be visible for you. The diagram is given in blue color and black. The blue indicates all about fetch and execution. The blue line in this picture is all about these two cycles, and black is all about decoding and write. Okay, See here in this modified hardware organization for pipeline execution, we have separate instruction cache and data cache. Okay, so previously we have seen about only the cache memory, where the instruction is fetched from the cache, and of course the operand will also be fetched sometimes from the cache or from the registers. And there are separate caches are maintained, so that instruction will be fetched independent of this data, and the data could be fetched from the register directly. Okay, so and see here PC is not connected to the ALU. So why it should connect, because to after each and every instruction fetch, the PC program counter has to be incremented. So here this separate unit is used to increment without the involvement of ALU. Okay, and for register transfer, for data transfer and instruction transfer, there are separate registers are used. Okay, DM are so data memory access register to access the data either from the register or from the ALU. So from the ALU, in the sense to get the index value for indirect addressing mode, so the index value or the offset could be fetched from the ALU. Okay, so separate registers data memory address register is used to fetch the operand value, and IMR, so instruction memory address register, this is used to fetch the instruction alone, and for that instruction we could get the data from here from the data cache. And see here, so we have separate register for memory read and write. Okay, so far we have seen about memory data register. So only one register that will go for either writing to the memory or reading from the memory. But here under a pipelining concept, we have separate registers for writing and reading from the to and from the memory, and that to happen independently via 3-bus organization. And here in the after fetching the instruction from the instruction cache, we have again maintaining the instruction queue. Okay, so the instruction queue for a fast access and reduce the stall operations. Okay, from the instruction queue, the decoder will identify what that instruction, and for that instruction to execute, this instruction decoder will give that instruction to the control signal pipeline, and this control signal pipeline will generate the respective control signals so as to execute that fetched instruction. Okay, so little modifications, those modifications are dealing all about independent operations. Okay, so only by means of independent operations we could achieve pipelining and get the better performance. And because of that independent operations in the pipeline, okay, so because of that architecture is modified to accept that pipelining implementation, and we could achieve these independent operations in that previous hardware organization. Reading the instruction from the cache and instruction cache, and reading or writing the data from the data cache, these are independent. Okay, these are not dependent. Dependency means we need to wait till the instruction gets fetched and then go for fetching the data operand, is it not? So this will go for fetching. Of course the instruction, only after instruction its respective data has to be generated, is it not? So while generating that data, the instruction this instruction cache will give the input to the instruction decoder to generate the respective control signals, and increment of PC is independent of ALU, and decoding the instructions will happen without dependent on any other hardware unit. And due to this 3-bus organization, we could give the input to the ALU straight away from we can pick up the input for ALU. Two inputs are there for ALU, that two can be picked up simultaneously from the two registers using the bus A and B, and data could be placed using another register, and performance of the ALU is independent. Okay, so why we need these independent operations? Then only the pipelining concept could be implemented in this hardware organization. Okay, and that's it about today's topic. It's quite interesting, simple, and we are at the with this our third unit is over, and I hope you understood the concept behind data path and control flow. Okay, so it means the hardware organizations are modified, so modified according to the implementation for pipeline execution. Okay, so that's it, and in next session I'll meet you in with your fourth unit. Thank you all.